Thank you, Yuri. Thanks for the invitation. I have not worked in this area for a while, so I'm putting my theoretical computer science hat back on, and I'm going to give you a sort of short talk without too many details because I know it's the end of the day, and I'll give you references to further papers if you want to hear more details, but please feel free to interrupt at any time with questions. And so I was asked to talk at this workshop, and so I saw the other people who would be talking, so I decided to talk on this topic. It's closely related to work that David Woodruff has done, and Jelani Nelson is of course an expert on fast Johnson-Lindenstrauss transforms as well. This is some work I did. I'm going to talk about a first paper I did joint with my student Ruhui Jin and Tammy Kolda, and then a more recent paper with my colleague Felix Kramer and his PhD student Stefan Bamberger. So I'll try to keep the slides a little simple. Why tensors, which is related to Kronecker products. A tensor is just a generalization of a matrix. A matrix is considered a 2D array. We can consider tensors D-way tensors, or I would just say a tensor of degree D of size n1 by n2 by ... nd. So this is a three-way tensor picture. Why these sort of data structures appear naturally in many applications, in spatio-temporal and temporal analysis, where we have a components versus a spatial dimension versus temporal dimension. You naturally have a three-way tensor. Polynomial kernels. So often we start with the linear structure, linear data structure, but want to boost it into a higher order tensor structure, such as with a polynomial trick, before passing the higher dimensional structures and through, say, a classification or a regression or any sort of learning algorithm in order to have a richer hypothesis space. Or where you do linear algorithm structure in the higher dimensional space, which then projected back into the original space corresponds to nonlinear structures induced by the polynomial kernel. Now, as you can just see from this three-way tensor, the storage and computational bottlenecks increase exponentially with the degree of the tensor, and we quickly approach the curse of dimensionality. In both trying to store these structures and then do computation with them. One application, although I'll be talking about something more general than this particular application, but it's a nice thought to have, is in tensor structured least squares problems. And so for doing tensor least squares problems, we can reformat the tensor into a matrix whose columns are each Chatry-Rao products, tensor products. So A is a matrix with many more rows than columns, and where each column has a degree D tensor structure, where all the NLs are the same in each column. And in doing a tensor least squares problems, we often want to solve for an x such that ax equals b here. And this is a really good application where n, the number of rows, is going to be increasing exponentially with the tensor degree d. And so very, very quickly, we want to ask, do we need to have all of these measurements n in order to get an approximation to this? Do we need to store the entire matrix A? The sketching paradigm, which I'm guessing you all know pretty well, is that instead of solving the original least squares problem exactly, we instead apply a sketching matrix S to each side of the equation and then solve a different least squares problem, a smaller least squares problem, sketch problem, and hope that the solution x hat to the smaller least squares problem is a near optimal solution in terms of having about the same least squares loss value as the optimal. And of course, with many fewer rows here in the sketch least squares problem. So for doing sketch least squares problems, when we don't assume sparsity structure of the matrix A. So when we don't assume anything, including erase the assumption of tensor structured columns, erase everything. The canonical fast sort of sketching matrix S for doing these sketchings is, it has many names coming from different communities. In this talk, I call it the fast Johnson-Lindenstrauss transform, or subsampled randomized Hadamard transform. It's a sketching matrix that is a product of three sort of base matrices. You start with either a discrete Fourier matrix or a Hadamard matrix. Randomize the signs of the columns of that discrete Hadamard matrix or discrete Fourier matrix, and then subsample a small number m of rows from that matrix at random. So this creates a short fat sketching matrix that inherits the nice n log n matrix vector multiplication from the orthogonal DFT or Hadamard. And so it's fast, and it serves a good enough approximation to the optimal sort of Gaussian sketching matrix. It's a pseudo-random matrix that has fast multiplication. The total cost of solving the sketch least squares problem scales favorably to the cost of solving the full least squares problem. And so the question is, at what cost? We're going to lose a little bit of accuracy for this improved cost. What is the cost? And so one way to try to understand what the cost of that is, but actually a more general setting than just the least square setting, is just to understand this basic, what's called distributional Johnson-Lindenstrauss property for a sketching matrix. And sort of behind lots of different concentration results involving sketches. So we say a random sketching matrix has the epsilon eta distributional Johnson-Lindenstrauss property for any fixed x. We get a 1 plus epsilon concentration of the squared L2 norm of the Sx around the squared L2 norm of x. And this holds with probability 1 minus eta. And immediately by the union bound, if we have this property holding instead for eta, but for eta over the size of any arbitrary set E of finite points, then we get that this property holds simultaneously for all points in the set E with probability 1 minus eta. So we're often, so I include this because I want to say in this distributional JL property, we really care about the dependence of the embedding dimension M needed to get this property, the dependence of M on the parameter eta. That's very important because when we do union bounds and so on, we sort of actually have to use a much smaller eta, exponentially smaller. So we really want a small dependence on eta of the number M. And so this second consequence is a sort of a consequence where applying this union bound along with some covering number estimates, we can not the union bound, but just standard covering numbers for a p-dimensional subspace, then we can uniformly get a near isometry of this sketch holding uniformly for a subspace. And this is not necessarily the optimal type of result one can get for embedding a subspace. It's just the direct consequence from the JL property. Okay, so the crucial question is how small can we make M? How short and fat can we make the sketching matrix S in order to have this property? And in particular, when S is the fast Johnson-Lindenstrauss transform or subsampled random Hadamard transform. And in this particular line of work, I'm quoting, they actually considered a more general class of fast sketching or sketching matrices where the orthogonal Hadamard matrix or Fourier matrix can actually be any orthogonal matrix, bounded orthogonal matrix, and actually any even more general, including also like convolutional matrix structures that satisfy a certain restricted isometry property. But the general idea at the end of the improvement by Habib and Regev in 2016 is that one up to log factors, the dependence on M is order log 1 over eta log n over epsilon squared. And I highlight the log 1 over eta dependence because this is the key parameter. We want this to be as small as possible. Well, it's the key for parameter when we start going to tensor structures and stuff to try to control. Does anyone have any questions? I can't really see you, so I'm getting the feeling though that you guys really know all this stuff already. So sorry about that. Okay. So those were some overviews of like the Johnson-Lindenstrauss property, the fast Johnson-Lindenstrauss property, and sort of the literature up to 5 or 10 years ago. And now we can consider a new type of structure that people have been considering recently to hold for, say, the input vectors, or if we're trying to sketch a matrix, the columns of the matrix. Again, let's go back to the setting where the columns of the matrix, or we want to embed p different vectors which have a tensor structure, a tensor product of degree d, where the lengths of the different factors are n1 through nd. Again, in this case, this n is going to grow exponentially with the degree d. And so even having any arithmetic cost that depends linearly on capital N, or any storage cost that depends on capital N, is going to be too large. That's a bottleneck, because it's like the curse of dimensionality. And so, as mentioned earlier, that one of the motivations where these tensors appear is that we start with vector input and then lift them into tensors via polynomial kernels. We wonder, inspired by that kernel trick, can we use implicit computations, just as one does when one kernelizes in machine learning with the kernel trick, to avoid forming the tensor input type of data in the first place. And instead, can we do the sketching implicitly, mode by mode, so that the sketching, storage, and arithmetic cost depends, scales linearly with just the size of the largest factor, little n, rather than the product of the factors, big N? And the answer is yes. If we carefully modify the Johnson-Lindenstrauss, the fast Johnson-Lindenstrauss sketching matrix in accordance with the tensor structured input. So how to design a good sketching matrix in order to sort of have these computations. A hint is that if the input vectors have these Kronecker product structure, really important property of the Kronecker product is this distributive property. And this hint suggests that if we do Kronecker products of sort of little fast Johnson-Lindenstrauss matrices in the right way and form a sketching matrix out of that, then it's possible that having that act on a vector with the same tensor structure can be done mode by mode. So sort of implicitly without forming the whole tensor or the vectors. And so this idea, I'm talking about this like it's my idea, but it's not. As far as I'm aware, this type, the correct way to form a Kronecker, what we call Kronecker fast Johnson-Lindenstrauss transform, in order to do the sketching correctly, was in this paper in 2018 by Tammy Kolda and collaborators. So they introduced based on their applications of trying to do these tensor least squares problems, the following Kronecker fast Johnson-Lindenstrauss transform. It's way too many words. KFJLT. It's not the best naming, but so if A has columns which are these tensor products, degree T tensor products, then if we do the process of tensor products of little NL dimensional discrete Fourier transforms, n by n, little n by n discrete Fourier transforms with randomized column signs, and take the tensor products of those, and then we have a giant matrix that we then subsample rows uniformly at random from the giant matrix. That not immediately clear, but if you work it through, you see that even though we're subsampling rows at random from the entire giant matrix, we can still, because of the distributive property of the Kronecker product, equivalently, the action of this sketch on the input can be done only mode by mode of the tensor input A, so that we never have to explicitly form these tensorized vectors explicitly or form the sketching matrix explicitly. And so the cost of forming the sketch when it has this structure, the punchline is that it scales nearly linearly, or with the sum of the mode, the tensor mode dimensions, rather than the product of the tensor mode dimensions. And so just like the kernel trick, which sort of operates in without having to compute explicitly the lifting, the polynomial kernel lifting, we can sort of do that sort of trick here to do the sketching implicitly. So this paper introduced this sort of fast sketching matrices for vectors with Kronecker structure, but it didn't prove, give any rigorous bounds for like the Johnson-Lindenstrauss property of this type of matrix. And so they conjectured in that paper that this sort of Kronecker structured fast JLT is indeed, does indeed satisfy the JL property due to experiments that they did. But you step back and you think, well, there's really reason to believe that we have to sacrifice something here. We can't expect to have the same nice embedding dimension where M just depends on the probability parameter eta, like log of 1 over eta. And that's because these Kronecker sketches are really using a lot fewer bits. There are not many bits, and they're not carefully designed fewer number of random bits. It's just we're only constructing, we only have little nl random bits associated to flipping the column signs of each of the little discrete Fourier transform orthogonal matrices. And then we have basically a Kronecker product of these random bits when we consider the sketch. And so compared to having a total, basically big N random bits, we have a much fewer. So we should expect that if there is a Johnson-Lindenstrauss embedding property for this type of matrix, it's not going to be as strong. It's going to degrade with the degree D. But the structure here really suggests that the method to analyze this is through higher order chaos, which is a very well established area of high dimensional geometry and probability for analyzing random structures where we have Kronecker products of IID of independent Rademacher sequences. And so I don't want to get too much into the technical part. So I just want to give you what we are able to show. And this is informal because I'm hiding log factors and hopefully just keeping the honest true dependence here. But we are able to show that the sort of Kronecker fast Johnson-Lindenstrauss transform satisfies the epsilon eta distributional Johnson-Lindenstrauss property at a number of measurements, which is given by log of 1 over eta to the D, where D is the degree of the tensor in the construction of the Kronecker FJLT, with a constant that depends on D, which can be of the form D to the D. So that's not good, but it's okay for small d. Log n over epsilon squared being the same. And so this is the sacrifice that we have log of 1 over eta to the D power as we increase the tensor degree or increase the structure. And this improves on many lines of work that considered these types of sketching matrices a couple years ago. Ale and David Woodruff and collaborators had a paper that includes lots of results, but just one of the results was that proving the Johnson-Lindenstrauss property for these types of matrices with a near optimal dependence, but with a log of d+1 dependence, 1/eta. And then we, around the same time, proved Johnson-Lindenstrauss property with a dependence log of power 2d-1. And then Malik and Becker had an argument showing this property for tensor structured input. And their argument's very, very simple and easy based on coherence. So that paper I recommend if you don't know anything about what I'm talking about. It's a good paper to get into sort of these sketching structures. It's very, very simple but elegant argument. And then Iwin and Rebrova et al. Also considered these tensor sketching structure. And they showed some improved bounds if the underlying matrix A with the tensor structured columns has a certain incoherence property that can improve everything, among other things. So this is the result. And let me know if you have any questions. We can show that this embedding bound is optimal. One cannot hope to get a better result like this. So this log 1/eta to the power d is a true sacrifice or loss that is necessary at the cost of the improved faster sketching. And then I guess the story might sound sort of bleak, but it's not actually bleak because there are several sorts of ways to start from one of these Kronecker JLT sketching and then build up a composite randomized sketch that has greatly improved dependence M and still has the good arithmetic complexity for doing the matrix vector products. So it's not actually a negative story. And so one of these constructions of composite tensor sketching construction in the paper of Ale et al. Considers sort of these recursive constructions of our KJLT, they call tensor SRHT, I believe. And they apply it to D divided by 2 products, and then recursively repeat this overall twofold products of the resulting vectors until only one vector is left. So this is a product of several types of these embeddings into lower and lower dimension. And by carefully putting this together they form a more powerful sketch that they showed has this nicer embedding power where M depends like log of 1/eta cubed and depends on the tensor degree only linearly. And so with the JLT, the Johnson-Lindenstrauss transform, using that as an intermediate result in place of the one they used, it's possible to improve this embedding dimension to have a log of 1/eta squared dependence. And I think this is a mistake. I believe that this becomes a constant depending on D. That can be like D to the like constant to the D. So that's perhaps one place where the results can be improved, the dependence on D. And I believe that having a Johnson-Lindenstrauss property with this sort of dependence on eta, like this one log 1/eta squared, implies a subspace embedding property that sort of has the nice dependence on the on the rank of the matrix that we're embedding, like the linear dependence on the rank, which is what one really wants way back up here in the sketching least squares. One wants a sketching matrix to have size that's sort of only linear in the statistical dimension or rank of the matrix. So there are many other possible applications of these Johnson-Lindenstrauss properties for these tensor structured sketches. Some possible applications might be in neural networks where tensors appear a lot and compression is important. Constrained optimization, where we consider more difficult sort of optimization problems with these tensor structured sketches than just least squares problems. Maybe we want to sketch semi-definite programs with tensor structure and prove guarantees there. All sorts of other optimization problems that we haven't explored yet. And then if we can do some sort of randomized higher order SVD for tensors using these sorts of sketches. These are the references to the papers I mentioned. This first paper is probably easier to read. The second paper gives the optimal embedding result. And so that's it. Thanks.